10 cosmic phenomena have forced physicists to reconsider everything. And today, we are revealing them all to you. What lurks at number 10 has forced physicists to confront their biggest miscalculation ever: the cosmological constant problem and dark energy's unexpected acceleration. In the late 20th century, scientists made a discovery that shattered their understanding of cosmic expansion forever. The universe was not just expanding, it was accelerating outward, driven by something completely unknown and utterly mysterious. Physicists had long assumed gravity would eventually slow the expansion, perhaps even reverse it into a cosmic collapse. Instead, observations of distant supernovae revealed the opposite. The expansion rate was increasing, defying every prediction and model. This mysterious force pushing everything apart became known as dark energy, comprising 70% of universal content. The cosmological constant problem emerged as the worst theoretical prediction in physics history, off by 120 orders. Quantum field theory predicted a vacuum energy density wildly incompatible with observations, creating an intellectual crisis of magnitude. Physicists struggled to reconcile why the universe's expansion energy was so incredibly tiny compared to theoretical quantum predictions. Every attempt to calculate vacuum energy from first principles produced numbers catastrophically larger than what astronomers actually measured. The discrepancy was not a minor error. It was an unfathomable chasm between prediction and reality, unsettling deeply. Dark energy seemed to permeate every cubic centimeter of space, exerting a gentle but relentless outward pressure constantly. No known particle or field could account for this phenomenon. The Standard Model offered no satisfactory explanation whatsoever. Some theorists proposed the cosmological constant itself, a term Einstein once called his greatest blunder, might actually be. Others suggested entirely new physics, perhaps extra dimensions or modifications to general relativity at the largest cosmic scales. The acceleration meant the universe's fate was not collapse but eternal expansion, growing ever colder and darker. Galaxy clusters would eventually drift beyond each other's observable horizons, isolated in an increasingly empty and lonely cosmos. Physicists realized their equations, so precise at small scales, completely failed to predict the universe's large-scale behavior. The dark energy mystery forced a humbling acknowledgement that 70% of cosmic reality remained completely beyond understanding. Experiments were designed to measure the expansion rate's change over billions of years, searching for clues desperately. Theoretical physicists proposed hundreds of models, each attempting to explain why the vacuum energy balanced so precisely mysteriously. Yet decades after the discovery, no consensus emerged. Dark energy remained physics' most profound and unsettling open question. The acceleration discovery earned a Nobel Prize, but the fundamental explanation continued to elude even the brightest minds. Some researchers wondered if the problem indicated a flaw in general relativity itself, requiring a revolutionary new framework. Others suggested anthropic reasoning, that only universes with this specific dark energy value could support observers like us. The cosmological constant problem represented more than a numerical discrepancy. It challenged the foundations of quantum theory itself. Physicists were forced to confront an uncomfortable truth about the limits of their knowledge regarding the cosmos' behavior. Dark energy's discovery marked a turning point, reminding scientists that the universe still held secrets beyond imagination's edge. Nothing has unsettled the scientific world quite like number 9, a phenomenon Einstein himself refused to accept: quantum entanglement and spooky action at distance. Albert Einstein famously rejected quantum entanglement, calling it spooky action at a distance, believing nature could not work. The idea that two particles could remain connected across any distance, influencing each other instantly, seemed physically impossible. Einstein argued quantum mechanics was incomplete, that hidden variables must exist to explain correlations without faster than light. For decades, entanglement remained a philosophical curiosity, a strange prediction with unclear experimental relevance or practical verification possibilities. Then physicists developed tests to distinguish true quantum entanglement from any possible hidden variable theory Einstein might propose. Bell's theorem provided a mathematical framework showing entangled particles violated inequalities that any local realistic theory must satisfy. Experiments confirmed the violations. Particles separated by kilometers exhibited correlations impossible to explain through any classical hidden variable mechanism. Measuring one particle's state instantaneously determined its partner's state, regardless of the distance separating them across space. This was not communication faster than light, but rather a correlation established when the particles were first entangled. The philosophical implications were staggering. Reality at quantum scales did not possess definite properties until the moment of measurement. Einstein's intuition about local realism, that objects have properties independent of observation, was experimentally proven incorrect and obsolete. Quantum entanglement became a resource for emerging technologies, including quantum computing, quantum cryptography, and ultra-secure communication networks potentially. Physicists realized the universe was fundamentally non-local, with distant parts connected in ways that classical physics forbade. The phenomenon forced a reconceptualization of space, time, and causality, challenging centuries of intuition about how reality operates. Entanglement experiments grew more sophisticated, eventually linking particles across continents, satellites, and even into space with astounding precision. What Einstein dismissed as impossible became one of the most verified and technologically promising aspects of quantum theory. The spooky action he rejected now forms the foundation for next-generation technologies that may transform computing forever. Physicists embraced the weirdness, recognizing that nature's rules at quantum scales defy human intuition built for macroscopic. Researchers worldwide have spent years wrestling with what emerges at number 8, a paradox threatening everything we know, the black hole information paradox and Hawking radiation. Black holes were already mysterious, warping space-time so severely that nothing, not even light, could escape their gravitational grasp. Stephen Hawking shocked the physics community by demonstrating that black holes are not entirely black, after all, surprisingly. Quantum effects near the event horizon cause black holes to emit radiation, slowly evaporating over incomprehensibly long timescales. This Hawking radiation implied black holes have temperature and entropy, connecting gravity, quantum mechanics, and thermodynamics in unexpected ways. But the radiation posed a devastating problem. It appeared to carry no information about what fell into the hole. If a black hole eventually evaporates completely, all information about its contents would vanish, seemingly violating quantum mechanics forever. Quantum theory holds information cannot be destroyed, only transformed, yet Hawking's calculations suggested it disappeared behind horizons permanently. This information paradox created a fundamental conflict between general relativity and quantum mechanics, two pillars of modern physics. Physicists proposed numerous resolutions. Perhaps information was encoded in the radiation itself through subtle correlations currently beyond understanding. Others suggested information might be stored on the event horizon's surface, a concept that evolved into the holographic principle. The holographic principle proposed that all information within a volume could be encoded on its boundary, revolutionizing space-time. Some theorists argued the paradox indicated black hole interiors did not exist as traditionally conceived, only horizon information. The debate raged for decades, with conferences, papers, and even famous bets between leading physicists about information's ultimate fate. String theory offered potential resolutions through fuzzballs, structures replacing the classical black hole interior with quantum string configurations. Others proposed firewalls, intense energy barriers at horizons that would destroy anything attempting to cross, violating equivalence principles. The paradox forced physicists to question whether smooth space-time itself was fundamental, or merely an emergent approximate classical description. Recent proposals suggest information escapes through quantum entanglement, between the radiation and the black hole's remaining mass gradually. The information paradox remains unresolved, representing the deepest tension between gravity and quantum mechanics in theoretical physics today. At number 7 lies a puzzle so fundamental it questions the very nature of reality itself, the measurement problem and Schrödinger's cat thought experiment. The measurement problem reveals that particles exist in multiple states until observed, defying all classical physics intuition completely. Physicists discovered that quantum systems behave fundamentally differently when measured, creating a profound challenge to objective reality itself. Schrödinger proposed his famous cat thought experiment to illustrate the absurdity of quantum mechanics applied to everyday objects. In the sealed box, the cat exists simultaneously alive and dead until someone opens it and observes the outcome. This paradox forced scientists to confront whether reality exists independently or requires conscious observation to become definitively real, somehow. The Copenhagen interpretation suggests that measurement collapses the wave function, creating one definite outcome from infinite possibilities instantly. Alternative theories propose parallel universes split at each measurement, with every possible outcome occurring in separate branching realities. Physicists still debate whether observation itself creates reality, or merely reveals what was always predetermined in hidden variables. Laboratory experiments with photons and electrons consistently demonstrate that unmeasured particles behave like waves spreading through multiple paths. The moment detectors measure which path a particle took, the wave behavior vanishes, and it acts like one. This observer effect suggests consciousness might play a fundamental role in shaping the physical universe at quantum scales, somehow. Some researchers argue the measurement problem indicates our mathematical models are incomplete, missing deeper underlying principles governing nature. Decoherence theory attempts to explain how quantum superposition breaks down through environmental interaction, not requiring conscious observers at all. The question remains whether particles truly exist in superposition, or our measurement tools simply disturb delicate systems irreversibly. Quantum computers exploit superposition to process information in ways classical computers cannot, making this paradox technologically useful today. The measurement problem continues challenging physicists to reconsider the nature of reality, observation, and existence at the deepest level. Despite a century of research, no consensus exists on what measurement means or why it fundamentally changes quantum systems. This enduring mystery reminds us that the universe operates on principles far stranger than our everyday experience suggests. Few anomalies have sparked more debate among cosmologists than what appears at number 6, a mysterious region defying explanation: the cosmic microwave background cold spot. A mysterious cold spot in the cosmic microwave background radiation spans a region larger than 600 million light-years. This enormous anomaly appears significantly colder than surrounding areas, defying predictions made by standard cosmological models and simulations completely. The cosmic microwave background represents the earliest light in the universe, released just 380,000 years after. Scientists map this ancient radiation to understand the early universe's structure, finding it remarkably uniform across all observable directions. However, the cold spot breaks this uniformity in ways that statistical models suggest should be extraordinarily rare or impossible. Some physicists propose the cold spot might mark a supervoid, an enormous empty region containing far fewer galaxies overall. If light travels through such voids, it loses energy through a process called the integrated Sachs-Wolf effect slightly. Yet even the largest known voids cannot fully explain the cold spot's extreme temperature deviation from the average background. Alternative theories suggest the anomaly could represent evidence of parallel universes colliding with ours in the distant cosmic past. Other researchers wonder if the cold spot reveals flaws in our understanding of cosmic inflation or the universe's geometry. Some scientists argue it might simply be a statistical fluke, an unlikely random fluctuation that happens to exist coincidentally. The cold spot's existence challenges the cosmological principle, which assumes the universe looks basically the same in all directions. Detailed surveys continue mapping the region, searching for unusual galaxy distributions or other features that might explain the anomaly. Every new measurement refines our understanding slightly, but fails to provide a definitive explanation that satisfies all physicists involved. The cold spot remains one of cosmology's most perplexing mysteries, hinting that our models might be missing something fundamental. Whether it represents new physics or just cosmic coincidence, this anomaly keeps scientists questioning their most basic cosmological assumptions. The debate surrounding the cold spot illustrates how a single unexplained observation can shake confidence in otherwise successful theories. Until researchers find a satisfying explanation, the cold spot will continue reminding us how much mystery still surrounds us. Deep space has delivered many mysteries, but number 5 stands out as one of the strangest and most baffling discoveries yet: fast radio bursts from deep space. Fast radio bursts are intense millisecond-long pulses of radio waves arriving from billions of light-years away mysteriously and unexpectedly. These cosmic signals release as much energy in milliseconds as our sun emits over several days of continuous radiation. Astronomers first discovered these bursts accidentally in 2007, while analyzing archived data from a radio telescope in Australia initially. For years, scientists debated whether fast radio bursts were real cosmic phenomena or just terrestrial interference from human technology. As detection methods improved, astronomers confirmed these bursts originate from distant galaxies, ruling out local sources definitively and completely. The signals travel through intergalactic space, becoming dispersed by free electrons encountered along their journey toward our radio telescopes. This dispersion allows researchers to estimate the distance traveled, revealing that most bursts originate from galaxies billions of light-years. Some fast radio bursts repeat at irregular intervals, while others appear only once, deepening the mystery surrounding their origins. Physicists proposed numerous explanations, including colliding neutron stars, evaporating black holes, and even hypothetical alien civilizations attempting interstellar communication somehow. The leading theory now suggests highly magnetic neutron stars called magnetars produce these bursts through intense magnetic field reconnection events. Magnetars possess magnetic fields trillions of times stronger than Earth's, capable of warping atoms into elongated cigar shapes theoretically. Recent observations detected a fast radio burst from a magnetar within our own galaxy, supporting this explanation with concrete evidence. However, not all bursts match the magnetar model perfectly, suggesting multiple types of cosmic events might produce similar signals. The repeating bursts show complex patterns that challenge simple explanations, with some displaying regular cycles spanning days or weeks. These patterns hint at orbital motion, perhaps indicating magnetars with companion stars or planets influencing the burst timing somehow. Fast radio bursts also serve as tools for studying the intergalactic medium, revealing hidden matter between galaxies through signal dispersion. Despite progress, many aspects of these mysterious signals remain unexplained, keeping astronomers searching for answers about their true nature. These cosmic phenomena remind physicists that the universe still holds secrets capable of surprising even the most knowledgeable experts. The universe holds countless secrets, but number 4 exposes a fundamental imbalance that shouldn't exist at all. The mysterious matter-antimatter asymmetry problem plaguing modern physics. When the universe began, matter and antimatter should have been created in perfectly equal amounts, annihilating each other completely. Yet here we are, surrounded by stars, planets, and galaxies made entirely of matter with no antimatter. For every billion particle pairs that vanished, one extra matter particle survived, and nobody can explain why exactly. This tiny imbalance, 1 part in a billion, is the only reason anything exists in the universe today. Physicists expected natural symmetry, but observations revealed a profound asymmetry that breaks all their most fundamental theoretical predictions. Laboratory experiments create matter and antimatter equally, making the cosmic imbalance even more puzzling and deeply frustrating for researchers. Several theories attempt explanations, but none can account for the sheer magnitude of the observed matter surplus fully. Some suggest unknown forces acted during the first fractions of a second, tipping the scales towards matter forever. Others propose antimatter hides somewhere beyond our observable universe, separated by unknown boundaries we cannot detect or measure. The standard model of physics offers no satisfactory answer, leaving this mystery as one of the greatest unsolved problems. Advanced detectors search for rare antimatter particles and cosmic rays, hoping to find clues about where it all went. Every experiment confirms the same frustrating result. Matter dominates everywhere we look, while antimatter remains impossibly rare and fleeting. This asymmetry challenges the very foundation of our understanding, suggesting missing physics beyond current theories and known principles. If matter and antimatter had perfectly annihilated, the universe would contain only light, no structure, no stars, nothing. The universe chose matter over antimatter through some mysterious process creating the physical world we inhabit and observe daily. Researchers continue hunting for explanations, running simulations and experiments, hoping to uncover why symmetry broke in this specific direction. Until we solve this puzzle, our picture of the universe's birth remains incomplete, missing a crucial piece of logic. The answer might revolutionize physics entirely, revealing new forces, particles, or dimensions we never imagined could possibly exist. What scientists discovered at number 3 has left theorists scrambling for answers, a particle whose mass defies all predictions. The unexpectedly light Higgs boson mass. When scientists finally detected the Higgs boson in experiments, they confirmed a particle that gives mass to everything around us. But the Higgs mass measured at roughly 125 gigaelectronvolts surprised everyone, being far lighter than expected initially. According to quantum calculations, virtual particles should push the Higgs mass to enormously higher values through constant invisible interactions. These quantum corrections should inflate the mass to trillions upon trillions of times heavier, yet somehow they do not. This discrepancy between prediction and observation became known as the hierarchy problem, frustrating physicists who expected internal mathematical consistency. Something must cancel out those enormous quantum corrections with extraordinary precision, balanced to dozens of decimal places somehow naturally. Such fine-tuning seems incredibly unnatural, like balancing a pencil on its point and finding it stays perfectly upright. Many physicists expected new physics would appear at higher energies, explaining this cancellation through undiscovered symmetries or additional particles. Supersymmetry was the leading candidate, predicting partner particles for each known particle that would naturally cancel the problematic corrections. But experiments found no evidence of supersymmetry or any other new physics at accessible energy scales, deepening the mystery. The measured Higgs mass sits in a peculiar range where the universe remains stable, but only just barely so. A slightly heavier Higgs would make the vacuum unstable, causing the universe to collapse into a lower energy state. A lighter Higgs would also create instability, suggesting we occupy a narrow Goldilocks zone that permits our existence somewhat improbably. Some researchers now wonder if we inhabit one universe among countless others, where only this mass allows life. This anthropic explanation troubles many physicists who prefer explanations based on fundamental principles rather than selection effects and coincidences. The lightness problem remains unsolved, suggesting either missing physics beyond current understanding or uncomfortable truths about cosmic randomness. Every new experiment searches for clues, but the Higgs stubbornly refuses to reveal why it weighs exactly what it does. Until we understand this fine-tuning, our grasp of fundamental physics remains incomplete, haunted by unanswered questions and troubling gaps. Astronomers mapping the cosmos found something deeply troubling at number 2: vast, empty regions challenging our models, cosmic voids, and the large-scale structure problem. Between clusters and superclusters of galaxies lie enormous cosmic voids, vast regions containing almost no matter at all whatsoever. These voids span hundreds of millions of light-years, creating a cosmic web structure that resembles soap bubbles or foam. Early universe simulations based on known physics predicted structure formation, but the observed voids are far larger than expected. The universe appears more clumpy and empty than theoretical models suggested, with matter concentrated along filaments surrounding enormous vacuums. Physicists struggle to explain how such immense voids formed so quickly after the universe began, defying straightforward gravitational collapse. Standard cosmological models predict smoother distribution of matter over large scales, not this extreme foam-like pattern we actually observe. The voids seem too organized, too vast, and too empty to arise naturally from random fluctuations in the early universe. Some researchers propose unknown physics during inflation created these structures, imprinting patterns we still cannot fully explain or predict. Others suggest dark energy behaves differently on these scales, pushing matter away from void centers with unexpected strength and consistency. The void problem connects to other mysteries about large-scale structure, questioning whether our cosmological model truly captures cosmic reality. Observations show galaxies avoid voids, as if repelled, clustering along walls and filaments in patterns defying simple gravitational explanations. The cosmic web's topology reveals information about initial conditions, dark matter behavior, and dark energy that current theories cannot reconcile. Each new survey maps larger volumes, finding more enormous voids that challenge our understanding of how structure grows over time. If voids formed through standard processes, we should see intermediate stages, but observations show surprisingly mature structure even early on. This suggests either rapid structure formation mechanisms beyond current models or fundamental misunderstandings about how gravity operates on scales. The voids might hold secrets about dark energy's nature, revealing how this mysterious force shapes space itself across cosmic distances. Physicists continue studying void properties, searching for patterns that might reveal missing physics or computational errors in standard theoretical predictions. Until we explain why the universe chose this particular large-scale structure, our cosmological theories remain incomplete and potentially flawed. The most alarming crisis in modern cosmology takes number 1, a discrepancy tearing apart our understanding of reality, the accelerating expansion rate discrepancy and Hubble tension. The universe is expanding faster than it should be, according to our most reliable mathematical models and observations. Two different methods of measuring cosmic expansion give us answers that simply do not match up at all. Scientists using light from the early universe calculate one speed, while nearby measurements give a completely different result. This mismatch has grown so significant that researchers can no longer dismiss it as simple measurement error or coincidence. The discrepancy suggests something fundamental is missing from our understanding of how the cosmos actually works and evolves. Perhaps dark energy behaves differently than we assumed. Or maybe gravity itself changes over truly vast cosmic distances. Some physicists wonder if we need entirely new physics to explain why these measurements refuse to agree properly. The tension has persisted despite increasingly precise instruments and methodologies designed specifically to resolve this troubling cosmic mystery. Early universe measurements rely on ancient light patterns that have traveled billions of years to reach our telescopes today. Nearby measurements use stellar explosions as cosmic yardsticks to calculate how fast galaxies are moving away from us now. Both methods seemed solid and trustworthy until they started producing results that differed by nearly 10% consistently. That might sound small, but in cosmology, a 10% difference represents a crisis that demands explanation immediately. Researchers have checked and rechecked their calculations countless times, hoping to find some overlooked error causing this frustrating problem. Every new dataset seems to confirm rather than resolve the tension, making this one of astronomy's most pressing issues. The answer might revolutionize our understanding of dark energy, dark matter, or the fundamental forces governing the entire cosmos. Some scientists propose we live in a cosmic bubble where physics operates slightly differently than in the universe beyond. Others suggest modifications to general relativity itself, though Einstein's theory has passed every other test thrown at it. This measurement disagreement has transformed from a curious anomaly into evidence that our cosmic model needs serious reconsideration now.